Hi, I'm Billy M. Martin, Principal Engineer for Cessna Aircraft Company in the area of electromagnetic protection. I'm also a supervisor for Cessna in our electromagnetics lab, as well as I've been on all the committees, HIRF committees that have written all of these rules to certify airplanes from a 787 down to a 172. So I was involved as a task group leader in writing these rules, as well as writing the test requirements to comply with these. So I would say Cessna does it just about as well as anybody in the world. So today we're going to talk a little bit about HIRF protection and design. How do I design my aircraft to meet the HIRF requirements? And what does HIRF stand for, by the way? Maybe I should talk about that a little bit. HIRF stands for High Intensity Radiated Fields. What that is man-made energy that's put into the atmosphere, whether that's from a radar system as you're landing the airplane, and all of us have seen radars going around as we land the aircraft, FM radio stations, HF radio stations, microwave, satellite link up, you name it. If we're putting energy into the air, then HIRF covers it. So, why is HIRF a concern? Back in like 1990 or 1980s, Airbus started to make what's called fly-by-wire systems. In other words, the computer flies the airplane. On the A380, the pilot flies it with a joystick. And so he's not flying it by cables and pulleys anymore. We have actuators and electrical current flow and computers that tell those surfaces where to go. And RF energy, electromagnetic energy, can interfere with those signals. Now, the military has known about that for a long time. And in fact, we'll talk about some various types of accidents that have occurred. But one of the primary ones was back in 1967. A Navy aircraft was landing on an aircraft carrier. Radar swept around. Connector was not, this is what they theorized, a connector was not connected properly, fired off an air-to-air missile, killed 167 sailors. As a result of that, every airplane that is built by the U.S. Navy or certified by the U.S. Navy goes to a facility called Patuxent River, Maryland, in which it's blasted with RF energy to prove that its systems will work. So the military's known about it at least since that time. We've been dealing with EMI aspects, electromagnetic interference, on our airplanes since we developed airplanes and had radios on them. So even back in the 40s and the 50s, when we were dealing with HF radios, we'd key the HF radio and electronics or electrical motors would start moving. So we've always had EMI issues, but typically electromagnetic interference is thought to come from the aircraft itself. I key my HF transmitter, the engine gauges start dancing. That's compatibility issues, interference issues. That's playing in the same sandbox, can we all get along issues, okay? HIRF is a different issue. HIRF is generated externally of the aircraft, and the aircraft flies through this field. So back in the early 80s and stuff, transport aircraft started to incorporate primary electrical flight displays and flight controls and things called FADECs, Full Authority Digital Engine Controls. Basically, electronics are doing things that analog systems used to do. So there was concern about it. And with the onset of the A320 certification, fly-by-wire control systems were used. So there was a concern about interference caused external of the aircraft. So what creates HIRF environment? Power. Power radiated from various types of high frequency and high powered radio transmitters, high gain antennas, or both. Or proximity. Power and proximity. I radiate a bunch of power and I fly the aircraft next to it. So this power and proximity creates energy enabling to couple into the aircraft. So here's a few requirements. A lot of times when we were writing these rules, people said, well, hey, I've been flying these airplanes forever. I haven't had these types of problems. Why do I have them? Okay, why do I have to go through all this expense and testing and hardening of equipment? So, as I mentioned, there were incidences in the military, and in fact, we've had incidences with F-16s, Tornadoes, well, primarily those two airplanes because they were fly-by-wire, F-111 fly-by-wire airplane too, as well as Black Hawk helicopters. They're kind of the poster child for HIRF. There were several Black Hawk helicopters that flew next to HF, like Voice of America transmitters, and they lost the aircraft. But there's been some for civilian aircraft too. There was an airship back in 1990, flew next to a Voice of America transmitter. It damaged the engine controls. They had to make a forced landing. Of course, a forced landing with an airship is it just kind of floats to ground. Okay. It's not that big a deal. But there's also been some helicopters, smaller aircraft that had some issues when they fly them next to electromagnetic fields. This HOA, I guess I put the same one. The Lytef AHARS had a heading reference that would roll off as you flew it or exposed it to RF fields. So there have been some accidents. There's several more. I just stuck a few of them up there. We have taken equipment into our chambers and discovered lots of problems with them. So, but remember, HIRF is typically a high amplitude transient device. So you'll fly through that field, you get a response, the tube blinks, something goes away or something, and the pilot just thinks it's a power glitch or something. So it's hard to distinguish the differences between those. But anyway, HIRF rulemaking was started back in the late 1980s and early 90s to address these issues because of the proliferation of electronic devices. And though we give the FAA a hard time sometimes about various rules and things, they were very foresight in this, okay? In the fact that they could see that the trend in aviation was to go pull, just like in everyday life. Imagine your life today without your smartphone, your BlackBerry, your computer, your printer, whatever. Electronics controls our life, the internet. Well, the same things happened in aircraft. Our airplanes are much smarter today than what they were 20 years ago. We fly in weather today that we would never have flown in 20, 30 years ago. Most of the avionics, the controls, all of that is done by electronics, by computers today, where 30, 40 years ago it was done by cables and pulleys and hydraulic lines, vacuum pumps. Now that's done by microprocessors. And electronics is very susceptible to electromagnetic energy. That computer or that electronic device doesn't care where that electrical current, voltage, or RF comes from. It appears that its interface is going to react upon it. So the FAA had a lot of foresight in that. So we should give them credit for that. Anyway, but there were some major issues when we were writing the rules for HIRF. Some of those were the HIRF environment. We studied over 500,000 transmitters, both in the United States, Europe, parts of Russia. They gave us information. Even China gave us information from all over the world. There was over 500,000 transmitters that were looked at for high power, for antenna gains, for transmitting frequencies, for duty cycles, etc. It was an extremely challenging engineering problem to come up with the environment and to accurately define what that environment should be as addressing all these databases. And then the other issue was, how do I apply that environment to the airplane, both the testing issue, okay, but also how do I define what the requirements are in regard to the equipment? And so we said, hey, the requirement should be based upon the functionality criticality. So in other words, if I have something up here that if it fails, I make a hole in the ground, then we better protect that so that never happens. So for catastrophic failures, the requirements are much higher than those for hazardous failures, for major failures, or for minor failures. So as the criticality of the failure decreases, so does the requirement. Only makes sense. Okay. So what are the HIRF requirements? There's a rule out there that basically says, and was published in 2007, and these are the parts. For part 23, it's 1308. For 25, it's 1317. 29, it's 1317. 27, 1317. And it applies to all functions, okay, and the systems that perform those functions. So the HIRF requirements are applied to the function and as a result to the various systems. So this just gives you an example of that rule, and I'm not going to read it. You can go read it yourself. But basically it says that, hey, if I have a system on an airplane that performs catastrophic functions, that function must remain available throughout the HIRF environment. So when I'm landing my airplane, okay, and I have another aircraft sitting there waiting to take off, and that 737's calibrating its weather radar, and I come flying by it with my old tail feathers or belly, soft belly, all exposed, and I'm exposed to that threat, I cannot lose any critical function during that entire duration as I fly by there. So during the exposure to the threat, no system that performs catastrophic failures, no function that has catastrophic failure conditions is allowed to be disrupted. And then for the other part of it, it says, well, hey, I have a display, a primary display, and I have a secondary display. So I have two systems that supply information of function of air data, for example. Well, since I have two systems and they're isolated, then this system could red X as long as this system maintains that function and vice versa. So it's the function that is critical to be maintained throughout the envelope. And if a system is disrupted, it must return automatically without the pilot doing anything. So that's just for critical types of functions. Then for hazardous, it says it can be disrupted during the exposure, but it must return. And it's talking about the function. Same thing with major function. And there is no requirement on minor function. So that's the requirement. Now let's look at the HIRF environment. 30 years ago when we were doing testing for EMI susceptibility and things, if we tested at all, those requirements were about 1 volt per meter. And it was primarily for onboard types of transmitters. So if I'm talking on my VHF comm, I'm not disrupting anything else. Again, playing in the same sandbox, nice type of requirement. So if we tested it at all, it was about 1 volt per meter. Now all of a sudden HIRF comes along and we're looking at environments that go up to 3,000 volts per meter. Now this is an external environment that's applied to fixed wing airplanes. So what it says is that if you come into my laboratory, we're going to do an attenuation measurement on an airplane and we're going to reduce the field by this external environment. But this is what the airplane is expected to see on its day-to-day operations flying throughout the United States and Europe. Now there's another environment that's called Environment 2, which is the environment in and around airports. And if you notice, some of those field strengths are exactly the same. And the reason for that is those transmitters, which are weather radar transmitters, by the way, are located on airports. And then if you're so unlucky as to fly in helicopters, then you can go up to like 6,000, 5,000, 6,000, 7,000 volts per meter. And the reason for that is helicopters fly wherever the heck they want to. We had a helicopter pilot on our committee, flew helicopters out to oil rigs in the North Sea, and we asked him, well, how far away do helicopters stay from various structures? He just kind of laughed and said, we fly as close as we can possibly get to them. So, as a result of that, remember that statement about power and proximity. Well, I may have a certain amount of power. If I can get real close to it, this is what happens. So, how do we protect against that? Well, in most cases for electromagnetic threats, 99% of electromagnetic protection can be accomplished by 3 very simple things for equipment. Good electrical bonding, good wire bundle routing, good wire bundle shielding. Okay? So what do I mean by that? Okay? Electrical bonding, in order to protect electronic equipment, I have to have a low impedance path to ground. So same way we talk about in lightning and stuff and having a low impedance for high amounts of current flow, it's also true for things like electromagnetics produced from HIRF or for current flows produced by lightning through the structure of the airplane. With a good electrical bond, okay, I create a low impedance path. And bonding means the process of making the necessary connections to provide not only a low impedance, but a nice surface area. Okay? Now, in HIRF, we can sometimes get by with a little less because the current is not quite as high, but for lightning effects, we can. And guess what? The same piece of equipment that must meet the requirements for lightning is the same equipment that has to meet the requirements for HIRF. So we have to have good electrical bonding, a good impedance path for that LRU to be bonded to. And if I remove that guy and put it back in the airplane, it is critical that that electrical bonding be maintained. Okay? And you can't get it by just a little piece of wire. Now, admittedly, I can take a milliohm meter and attach it with a little piece of 22 gauge wire and put a strap across there and make that measurement. It says I'm good, I meet the spec, and off we go. But the intent is what's important, not the number. The intent is to provide a low impedance, low capacitive coupling point to ground. And you can't get that by single small points. So with equipment, we want to make as large a surface area electrical bond as possible. Okay? Good electrical bonding ensures there's a low impedance path to ground, reducing that voltage that's felt on the interface of the equipment. That equipment doesn't care where that electrical current or that voltage comes from. It can be coming from the LRU feeding it, or it can be coming from HIRF for indirect effects of lightning. All it knows is that I have a voltage there, and it will act upon that voltage. And with HIRF, it can carry current inside there, demodulate. And if I know the frequencies of operations of equipment, I can screw it up. It's as simple as that. In a previous life, that's what I did. Okay? If I know the operation, I can mess it up. High-power directed weaponry, all kinds of RF energy the government uses. We don't go in there or I'd get in trouble. But basically, if I know the frequencies of operation of a piece of equipment, I can make it lose its brains. So that's what HIRF does, okay? It couples into equipment and it makes it lose its brains. And so we have to protect it against that. So there's 4 ways, again, to provide good electrical bond in regard to equipment installed in our airplane. One is a direct, and by far the best, it's a direct metal-to-metal LRU to structure bond with as large amount of surface contact as we can get. The second way is to use bonding jumpers or straps, and in some cases we have to use bonding straps. We have a box that's an air compressor that's mounted upside down onto a plastic case and with isolator jumpers. We can't mount it directly metal to metal, so it's critical we put a bonding strap on there. And the reason why it's critical, because if I put a wire bundle on there that has shields, that shield current goes to that connector to the case to the aircraft frame. Any one of those connections being broke, I lose the current path, and I cannot protect wire bundles or equipment without good electrical bond paths. The other way is joining structures with driven rivets, and that's really good, especially if I got a bunch of them. Okay, so especially if that rivet is displacing metal. In other words, I'm putting a rivet into a smaller hole and I'm hammering it and I displace that metal and I get good edge contact around there. Lots of those rivets provide multiple current paths. The requirements within the maintenance manual are in section 20-10-2 for electrical bonding aspects. Oh, I'm sorry, this is for electrical bonding aspects is 20-10-2. And basically it shows you all the different ways to do the bonding, and it tells you how to connect them. All right? So good electrical bonding. Now the second way is through wire bundle shielding. So wire bundle shielding and routing. It is impossible to shield against magnetic field effects without a circulating current. Right? Most of us, or a lot of people, were in Boy Scouts or stuff as younger age, and if you take a piece of copper wire and you hook it up to the terminal of an amp meter and then take a magnet and run it by it, you see that current meter doing like this. That's because those lines of flux from that magnet are cutting across that copper conductor, creating a current flow. Well, when an airplane flies through a high electromagnetic field, creates a time amplitude response, that magnetic field propagates through the windows, the cracks, the doors, seams, whatever, and that energy seeps in, and that magnetic field cuts across those conductors, whether it's wire bundles, hydraulic lines, whatever. And as a result of that, it creates a current flow. It's called the right-hand rule. The magnetic field's going this way, current goes that way. Now, if I put a shield on that wire bundle, I create a current flow going the opposite way. And if it's a perfect shield, it cancels that magnetic field out 100%. So it's impossible to cancel electromagnetic fields without proper shield terminations at both ends of the wire bundle. Another thing that's really critical is that when you go from one junction of the airplane together, we design it so that we terminate those shields into that connector so that energy isn't propagated from the nose bay into the cockpit, or from the tail cone into the fuselage, or from the belly fairing into the fuel tank, or from the belly fairing into the cockpit. We terminate it at those bulkheads, or from the engine through the firewall. So each one of those points, it's critical that we electrically bond the connector, and the shields are terminated properly into the connector, and therefore the currents will flow into the ground plane. So the main coupling route for electromagnetic interference is cable bundles up to about 400 megahertz, and probably even up to about a gigahertz. Now, a lot of you don't know what that is, and you don't really care, okay? But RF energy is dimensionally driven. And what that means is it has a certain wavelength, okay? And that wavelength will couple on and resonate at certain frequencies. The wavelength at 300 megahertz is 1 meter in length. So at 1 meter, a wire bundle at 1 meter, that full wave resonance will occur at 300 megahertz. And what that means is that wire bundles, antennas don't create energy, but they effectively gather it, okay? It's like if I have a perfectly round balloon and it's filled with air and it's a perfect circle. That's the same as what's called an isotropic antenna. It radiates perfectly in all directions. Now imagine I take that balloon and squeeze it, and now I push the air in one direction. I didn't create any air inside of the balloon, but I directed it differently. That's what an antenna does. It directs, it gathers energy effectively in certain areas. Wire bundles become directivity, or have directivity associated when certain wavelengths resonate on them. So they effectively gather energy in. Don't create it, but it gathers it in. So the most important way to protect the equipment in those frequency ranges is by shielding the wire bundle. You cannot protect the equipment without proper shielding. And termination of the shield is just as critical. Now, if I have something that's going to make a hole in the ground, a catastrophic failure condition, we typically certify that with an overbraid and what's called a 38999 connector, in which it's a 360-degree back shell where those terminations are made into that, and it creates a complete Faraday cage. Perfect conduit for cancellation of that field. However, that's not always practical, and it's not always necessary. Okay? So again, antennas, effective gatherers of energy. They don't create energy, but they effectively gather it, and they do it at certain frequencies more efficiently than others. So like a quarter wave dipole or monopole has a gain of about 2.14 dB, a dipole about 2.4. What's that mean? It means it gathers energy equally. Okay? It's the same sort of thing that happens with a mirror, let's say. If I shine a light directly onto a mirror, I get a perfect reflection. As I move that mirror sideways and reflect that energy, I don't see as much on my light. It's because that energy isn't as reflected, it isn't coupled as well back into my eyeballs. This just shows some ways to terminate shields, and in each particular case, you notice we terminate the shields into a connector and down to the ground. 38999, 360-degree back shell is the best, okay? And it's typically used for fly-by-wire type systems where the consequences of failure are the highest, all right? But it's very expensive and they weigh a lot. And weight is a premium on an airplane, as you know. So we don't use those unless we have to, where the consequences of failure are such that we insure. We also, by the way, test without that overbraid on there. So the overbraid's used for margin. So we provide additional protection on our airplane. What we typically use is an external pigtail. But it's critical that those pigtails are maintained properly and terminated properly into the back shell that provide that low impedance path to ground. Sometimes we can't terminate into the back shell. We have a plastic connector on the back side of an LRU. So we have to jumper off of that connector to a ground point. It has to be long enough for me to pull the box out of the instrument panel. So we have to make it longer than we want to. We don't build Faraday cages at Cessna. We build airplanes. Okay? But by engineering into the aircraft design and maintaining that, we can provide sufficient amount of protection to ensure against these threats. But we have to find that compromise. We can't put everything under 360-degree back shells. So we have to use pigtails so to minimize that weight. But in doing that, it's a compromise. It's a trade-off. And if we don't maintain them properly, we lose that battle. So it's critical that they're maintained properly. And then the other ones down here should never be used because now I've put the shield on there. I've incurred the cost of the shield. I've incurred the cost of the pigtail. And then I drive that inside and let that RF energy radiate inside the box to screw its brains up. And then this one down here, this is an antenna. This is a radio receiver. And in the cases of a lightning strike, I'll drive large amounts of current down there and let all that blue smoke that makes that box work out. So this is, you should never ever do either one of these two. Okay, the wire bundle shield repairs, again, it's critical to maintain the integrity of those shields. There's guidance in there given to you on how to inspect those and how to look at them. You know, you're looking for bird caging, looking for looseness of that connector, looking for those shields not terminated properly and giving you the right end. Doesn't do any good for me to spend all this time, money, and cost to put shields in there and put them in if they're not maintained. Because if that connector, if that screw comes loose at that back shell, then I lose that low conductive path to ground and I no longer cancel those magnetic fields. So wire bundle energy, it's dimensionally driven. A very good example of this is if you're driving in your car, okay, and you're listening to the AM radio and you drive underneath the bridge, the radio goes out. Okay? If I'm listening to the FM radio, I drive underneath the bridge, I continue to hear the radio. The reason for that is frequency. The AM radio is a very low frequency, therefore has a very long wavelength, and it physically can't fit underneath the bridge. The smaller or the higher frequency FM radio has a smaller wavelength. I drive underneath the bridge, the wavelength can fit underneath the bridge. Okay? It's physical. It has a wavelength. It has a physical dimension. That means the longer and the larger the antenna, okay, the greater the effective area it has for gathering energy. If you ever go down the highway and you see these big satellite dishes and they just have these huge dishes, well, the reason for that is they need a large amount of gain to direct that energy up to a satellite thousands of miles away. So that antenna has a very large surface area. Same sort of thing with our wire bundles in our airplanes. That's why it's critical, okay, to reduce the effective area of that antenna. To reduce it, we can terminate the shields at bulkheads, thereby shortening the overall length of the wire bundle. We can route wire bundles down to the ground plane, reducing the physical, what's called the inductive loop of those wire bundles. Anyway, to ensure that we reduce that area, we route the wire bundles. Let's give a couple examples of that. If you look at this wire bundle coming off of this ground plane, and each one of these lines are those flux densities I talked about with magnetic field effect. As I pull that wire bundle away from the ground plane, it's exposed to a higher level of flux density. That's called the inductive loop aspect. As I pull it back into the ground plane, I reduce it till finally I put it in a metal conduit, what's called a Faraday cage, and I completely shield it from that. Okay? So let's just give a practical example of how that happens, because that pictorial doesn't work very well. Now this example is about lightning, but it's exactly the same thing with HIRF. It's a magnetic field coupling of loop area. What I had was a generator in which I simulated a strike to the airplane. And I'm going to measure the open circuit voltage on an interface going into a piece of equipment. So I simulate, not exactly, drive. I put about 1,000 amp current flow onto this ground plane. And I route the wire bundle well up above the ground plane. So we think back to that wire that's off of the ground plane and exposed to a large amount of flux density. So I route the wire bundle up above the ground plane or the aircraft surface. I take the shield and I don't terminate the shield at both ends, and I measure the voltage at the interface, and with a simulated 200,000 amp strike, I get 10.5 kilovolts at the interface of that equipment. Now that piece of equipment may have been used to seeing millivolts or maybe even a few volts, but it dang sure is not used to seeing 10.5 kilovolts. So whatever's on the inside of that equipment probably let all that blue smoke out. So now I do exactly the same measurement, except for this time I put the wire bundle down on the ground plane and I terminate the shield. I run the same measurement again and I get 99 volts. Now I have a 1,000 to 1 improvement simply by terminating the shield properly and routing the wire bundle next to the ground plane. So what that means is that simply by engineering into the aircraft and taking advantage of the metal structure, making sure the shields are terminated properly, I can protect my equipment without driving a whole bunch of cost into the equipment itself. I take advantage of the installation, but that only works if it's maintained. So conclusions is that the worst case was 10,000 volts, best case was 100 volts. I got a 40 dB improvement. And by using proper wire bundle shielding and routing and electrical bonding techniques, I was able to get 40 dB of equipment. So cable bundle shielding, by shielding the wire bundle, you create a nice low impedance path. You want the energy to stay on the outside of the shield, not on the center conductor, not going into the LRU. But I often get this argument from people that say, well, I can't shield every wire in the airplane. It costs too much money, it costs me too much weight. And you're exactly right. It's not required to do that, okay? Because as we route our wire bundles together and we put shields on them, there's a point of diminishing returns. So as an engineer, I look at those installations and I try to say, well, okay, I don't have to shield all these lines. Can I reduce some of them? And in fact, we can, okay? Now, a lot of times we put more shields into the wire bundle than what this says is necessary because of the criticality of systems. But this is an interesting phenomena in the fact that as I increase the amount of what's called adjacent low impedance conductors, then that overall wire bundle starts to appear like a single wire bundle, and I reduce the overall effective coupling due to shielding effects. And that's what this says. I have a wire bundle in the airplane, had 10 wires on it. I measured the open circuit voltage on the first one with no adjacent shields. As I start adding shields into it till I get out here to 10, I see an exponential effect as that wire bundle falls, or the coupling effect falls off. So what that means is I reach a point out here to where it flattens out. So adding more shields doesn't help protect the equipment anymore. So as an engineer, I can look at that and try to reduce the overall weight on the airplane by only shielding things that are critical. So from a maintenance standpoint, it makes it even more critical to maintain the ones that we have on there in a proper configuration. Okay, conclusion. A lot of people think they don't, because you can't see HIRF. It's not like lightning that strikes the ground. You can see that lightning strike. You can see that bright flash as it strikes the airplane or a tree or a house. So you know that's a real threat. and we got to protect against. You talk to most people and say we should protect our airplanes from lightning, they say yes, we certainly should. If you say we should protect it from HIRF, they say what? But HIRF is a real threat, and it can disrupt and cause our equipment to fail if the equipment is not designed properly, it's not installed properly, and it's not maintained properly. But the majority of that protection can be achieved by good electrical bonding of that equipment, good wire bundle shielding, and good wire bundle routing. All are critical to maintain the protection on the airplane. So when you're working on the aircraft and you pull something out, you have to make sure when you put it back in there it's electrically bonded. If you have to work on a wire bundle and have to disassemble, it's critical that the shields are terminated properly. And it's also critical to route the wire bundle as close as possible to the electrical ground plane or metal. So take advantage of all the surrounding structure, make sure you electrically bond things, and make sure you maintain the shield integrity. And thank you very much. And that concludes the HIRF lecture, and I hope you found it beneficial.